Okay, let's start our class. So, in the last class, we mentioned the unsupervised learning. Specifically, we mentioned the k-means clustering. So again, I want to give a very quick review. The main difference between the supervised and unsupervised learning is that for supervised learning, we do have a label Y. So that, here you can see they're colorful, meaning that, when these are training data. When you get the training data, you know the label of each data point. While in the unsupervised learning, you do not know the labels. So for example, here, here I just, without the loss of generality, I make all the points to be dot points. This to indicate that you just know, the coordinate X, Y, that's it. I mean, for each data point, but you don't know exactly what they are. So that's the thing. So in general, unsupervised learning, I should say in general, a clustering problem is based on a given or a predefined dissimilarity measure function. I need to, cluster, manually give the labels. Formula, I should say, give the clusters for each data point, and then use this result to, kind of like classify or make a prediction for all future data. Okay, so we mentioned the algorithm, the key algorithm of the K-means algorithm. This is very important. You'd better know how to read it, and you'd better know how to code it manually. Because this is, in my personal view, this is a very good example to learn both machine learning and also make it's pretty simple to be honest, and make a practice in the coding. Okay. So here is the algorithm, and here is the stopping criteria. We mentioned the three types of stopping criteria, and in practice, you may use all of them. I mean, it can be combined, use an OR function to see whichever is reached first, then it's going to be stopped. That's it. Here is a step-by-step illustration of the k-means clustering, and you can see initially centroids are here, and then cluster assignment, centroid update, cluster assignment, central update, repeat. Here, since I already know the result that the iteration just need four steps, and hence I didn't really give you the stopping criteria here. As you can see, in iteration 3 and 4, the centroids, the results are exactly the same, meaning that it will no longer get updated. So of course, I mean, you don't want to have a dead loop. So of course, I'm going to stop here. But in a practical problem, you probably will not, meet so you be so lucky to be honest. Actually, this is one of the special case in which there are see it, so that you can just use a combination of these three stopping criteria, and I mean, it includes this situation. Okay, so and then we mentioned this example, which is how do we, instead of manually writing the k-means algorithm, how can we apply the k-means algorithm directly via the scikit-learn library? And it's from clusters k-mean. And here I used make blobs, this one to generate, those kind of data, forming those kind of blocks actually. And then I remember we stopped here. So here's one thing. I make the theme of this slide to be applications of k-means clustering from clustering to classification. So here I use a cited classification, meaning that it's not a real, I mean, classification. Strictly, this is not really a classification. It should somewhat be a prediction of cluster membership rather a true, like a real classification. However, the idea is exactly the same, which is we first, I guess I could just, so this is a given training data. First, we use a k-means clustering algorithm to get the clustered, to get a centroid. And then using those centroid, you know what, I can do a p color mesh, right? So in this p color mesh, I can, just simply based on what? On these centroids, I can fix these centroids. And then what I can do is, for I can generate like the linear space in this area, and then use the linear space. Remember, if we train the k-means clustering model, we will have a model parameter. We'll have a model, right? And then in the model, I can use the model that predict. So for each, I will generate a linear space in this, use mesh grid. So for each point, I will make a prediction, and then use the prediction. After it, I will have like the, like cluster region prediction matrix, and then I can p mesh plot based on this the whole matrix. So that's the whole that's the idea for from clustering to classification. Again, the main idea is based on the training data. I first do clustering, then I do centroid, then I train the model. Then I will, for any point in this, plan, I can just predict it. Of course, here is, to make it more, easier for us to understand. So I visualize it in the real problem. You don't have to. It's simply you can just apply this idea. So that's how you do. Okay, let me just code this part. Where it is? It's here. Where it is? Okay. So what I'm gonna do first of all is just let me just copy and paste. Lazy to do what? Okay. So first of all, I need to generate the training data. Let's say without a label. Although I will get a label, but it's just for cheating. I want to really use it. Make make blobs, and then and sample equals to I guess I use the same thing. Yeah, almost all of these are the same actually. I'm not sure. Can I just copy and paste? Let me see. Maybe I can simply just copy and paste. Oh, sorry. I remember they're pretty similar. Let me see here. Okay, so here, number of clusters. What number of clusters for here? I'm not sure. Okay, here we apply three, I believe. Yeah, three. Number of clusters equal to three. Okay, so now have the k-means clustering cluster equal to three. Here, assuming I know, the number of clusters k equal to three. Okay, so now I have this, and then I'm gonna create this one, and then I'm gonna subplot. Now I'm gonna plot three, which are the original data, the clusters, and then the decision region of the clusters, and then I'm gonna have this training data legend original, yes, the same thing. And then I'm gonna subplot the data with, of the swimming clustering for the data sets, which is correct. Let me see here, X data predict, wait, 1 minute, 1 minute. Why predict? Okay, here's very careful. Here, be careful. It is not a y equal to zero. Okay, instead you must use y predict. Why? Because I mean, here we have the y's just because, for the reason I need to apply this make blobs function. So I need to put a y there. But the truth is you should pretend that I don't have the y. So this y predict is the predicted value of the clusters for each data point, which is not necessarily the main, I mean, correct. It could be, a miss, clustering, Okay, so here I should use y predict so that I have x, y, 1, 2, 3. Here is 1, 3. And then let me see here. Okay, here's the same. So here I'm gonna plot all the centroids and then use a KP precision equal to 3. PLT dot show. Okay. Oh, did I just I should add this anyway. Okay. So now I have this let me see here. Why don't show the huh? I applied here. Why don't give me a second? I probably need to restart the kernel. Where's the kernel? Restart kernel. Okay, let me just reload the whole page to make it easier. Okay, here we go. Yeah, here. Okay, here we go. Sometimes I don't know. Sometimes the server is pretty weird, and I can tell you I forgot which day. There was a day, Tuesday, Wednesday, probably yesterday, when I was writing another code. I mean, another project for fun. and then accidentally it just done run, and then just you're gonna see the status something here, not here. There was a status something like just in the queue, just waiting. Even if I remember I put a print X like this way, it just queue in the queue. I mean, it doesn't run. I mean, I don't know. I just refresh a page for many, many times, but it doesn't work. I even prepared that if, let's say, if in today's class, the server Anaconda server dies, then I'm gonna use my, remember I told you you can install a navigator, which is this one, so that it's gonna be installed in your computer, local computer. So you don't you worry, in case the server dies or in case you don't have the internet or something. So yeah, that's the thing. But the thing is, sometimes it's just weird. Sometimes if you feel really you don't understand, you can just simply refresh the page or just restart the kernel. Okay, so where are we now? Okay, we're here. So we've already printed the training data, printed the training results of the three means clustering algorithm. So the next one, what we want to do is that I want to get from the clustering to the classification, right? Then make a classification. Again, I use the quoted classification because it's not a real classification. Let's say, and subplot the, let's say, cluster. Let me use cluster here, cluster region here, instead of classification regions because it's not a real classification. Okay, so first of all, I can add a big dot, add a subplot 133. And then what I'm gonna do, so here, in order to to get this one. So I already have this, right? So these points, all the points, what I can do, I can use it model.predict and then generate the two the mesh grid and then use the Ravel, make them to be flat, right? As we've done many times in this class. Linear space. Let me see. Let me see what number did I use? 3. Okay. Plus my, I mean, again, it's just a boundary. Again, this is not really serious. It doesn't matter. I want to use 3. You can use 0 even or whatever. The key is just to make it looks beautiful. Because I'm giving a class. That's the point. It's not that serious actually. Okay, so after generate this match grid, I'm gonna have, generate the points, right? Let's say a cluster region predict equal to model dot predict. I'm gonna predict all the points, generated by the match grid, np dot array dot transpose. Okay, so now, wait a minute. I probably need one thing here. Yes, I will need a color map. So I'm gonna from map plot lib.colors import listed color map. Okay, so now I'm gonna, let's say, cluster region color equal to listed equals to listed color map, and then use our three favorite colors, which is light orange, light green, and then like blue. Oops. Okay, so now I can use the PMesh grid, and then finally x dot p color, not PMesh grid, p color mesh, sorry, x1, x2, cr predict. Come on. Okay, dot reshape, then x1's shape. Of course, you can use x2's shape if you want. I mean, it really doesn't matter. And then see here, KP problem, upper size equal to 12, I guess. Where it is. No, sorry. Here I'm talking about P mesh grid. Yeah, so I don't need any other things. I just need a P map equal to CR color. Okay, so now I'm gonna X plot. So I'm gonna just copy and paste from here. X plot this with this. Okay, so finally I just need with a title here. The title, let's say clusters, the cluster regions. Okay, then here there we go. Here. Wait. That means something's wrong. Wait a minute. Did I put three? Yes, one, three, three, one. Oh, that's one, one, three, two. And then let me see here. One, three, one. Okay. Let's give it a tight layout. Okay. Here we go. So, for first of all, you might see, oh, why the results are different from the what, which is very normal. Why? Because it's here. We randomly generate those kind of blocks, and hence, every time, now it looks like triangle, right? I run it again, for example, and you can see, you can see there's a difference, right? But the meaning of the algorithms are exactly the same. So again, the idea is first we got original data, no labels. Then we run a clustering. Three means clustering algorithm. So I get these three clusters, and then use the model itself. I generate a mesh grid, and then for each point of the mesh grid, I can make a corresponding prediction. Prediction means what is the label? It's like kind of like a classification, and then to visualize that, to make it more clear, I subplot the cluster regions. So yeah, that's it. So this is what I meant, here, which is from clustering to quoted classification. So that's the meaning. It's actually pretty interesting and practical in those kind of real world examples. Any questions here? No. Okay, so let's go forward. The next one is something interesting, really interesting. It's called image segmentation. First of all, I just want to make sure, I want to make it clear that image segmentation has many methods. Even if you're in computer science, there are actually many traditional methods. By traditional methods, I mean those kind of manually, input existing algorithms instead of machine learning algorithms. There are really a lot. Like I remember, like 20 years ago, at the time when I was a student, we really need to learn those kind of things. The good thing is that when now you have machine learning, it's much more powerful because it is kind of like flexible. It's not a given fixed something. So that's the thing. First of all, let me introduce the concept in case you're not familiar with that. So image segmentation means partitioning an image to multiple regions or segments that have relatively homogeneous, visual characteristics. These things are often, pixel based, especially like RGB colors. And the main purpose of this is, first of all, to simplify the image to highlight the significant part. Based on those kind of characteristic, let's say RGB difference, color difference, or something, the second application can be, for example, serving as the initial step for further processing. For example, like objective detection. Later we'll see this. For example, this is the MR scan of someone's brain, and clearly, this is original image. This part is wrong. You can see it's actually unfortunately a tumor. Then from the original image, I mean, of course, you can see something that's not that clear. In contrast, as you see here, after humans clustering, it's super clear. You see what I mean? Because you can have a standard image, in which it should be just all dark here, and then you can compare it with the standard image. Then you're going to immediately detect, hey, something's wrong here. Of course, here we have 2, 3, 5, 10. For example, in 10 means clustering, you can see there are more those kind of characteristics here, for the features. And then I'm not a doctor, but if you know many things about, like the brain science or something, you can analyze. For example, based on the color or something, like the shades there, you can even detect maybe, what kind of the tumor and how to handle something like that, given enough data. So this is something called serving as the initial step for further processing. And another thing is to reducing storage space, of course, because before, for example, here I have, I don't know how many colors. Let's say suppose I have 50 colors. Here I only have two colors. Of course, the size, of the image will be much smaller. So these are the things. Something I want to mention here is suppose the original image contains n pixels. Typically, the n is a pretty large number. Say 1,000 by 1,000, it's 1 million. Each potentially having a unique color. So, in other words, this in other words, here I should have kind of like n. I could have n colors because considering RGB, right? I mean, 256, 256 is 2 to the power of 8. So 256 power of 3 because each RGB, each one is 256. So it is actually 2 to the power of 24. Actually, I don't know what is the number for 2 to the power of 24, but it must be a pretty big number. 2 to the power of 24 is okay, 16 million. Actually, not that bad. So if you use RGB, then technically this is the maximum number that I can have. Of course, you don't have to really use RGB. Like nowadays, computers have can render many more colors. The number could be billion, even billion wise. However, the good thing is for if I apply the K-means clustering, then I can limit the number of colors to be at most k. Say, for example, this is the original number, my k can be 10. Think about this. From this 16.77 million to 10, how many times, I reduce the storage, right? So that's the thing. Actually, the what in extended reading here, I actually showed some example. I believe I even I believe I even showed the estimate. However, to be honest, these examples some formulas I derive it, but these examples are borrowed from the book. I believe I cited here. So that is the thing. It can even actually give you here you go. It can even give you a compressed ratio, which is something from let's say 24n to approximately 24k plus n times the log 2k. Again, n is a very big number, k is a much smaller number, so you can see the comparison. It's a you know it's a pretty good compression ratio. Uh, and I don't know whether if you used, like a long time ago, Windows, kind of Windows 95, Windows 98, then Windows 2000 and 2000 Server, those kind of, PC, Microsoft system. A long time ago, there's something called a zip, WinZip. After it is WinRAR. And if you put something, just make a compression. I forgot what's the name. It was many years ago. I mean, really 20, 30 years ago. Uh, Basically, it's pretty, at that time we were kids, it was pretty magic, which is it can, help you to compress a image to a much smaller, like from 1 MB to maybe 100 MB or even 10 MB, those kind of things. And then it's actually by this kind of like a clustering algorithm actually based on this. And the result was pretty impressive, I would say. At least at that time, from a kid's point of view, it was very nice. Of course, at that time, I didn't know image segmentation. I also didn't know image clustering, but the result was actually, by this algorithm. And this technique is what they used in many applications, so like image enforcement, yeah, enhancement, sorry, image compression, radiology, something. Okay, let's have a look at just directly with it. Let's have a look at the thing here. Let's see how can we just play with that. And let me use another one here. I don't need it, so I can just copy and paste those kind of things. I don't need this. And I do need more things. I believe, okay, yeah, let me run it in case I need more. I will just load more. So here I first define a path. Path is going to save, the image because I have many other examples. So I'm going to define the path like this way. You can, of course, I believe, let me see here. I believe I wrote it as a function. Yeah, you can definitely, make it as a function. Here, in the class, I'm just a bit lazy so that, and I want to show step by step, especially this reshape and those kind of functions. That's why in the class, I would prefer to write it, as directly, as cells. But from the point of view of like a practical view, you are highly recommended to make everything to be like functional based or class based to make more robust. Okay, so here I have the path. So I'm gonna first get the image tensor, image equal to plt dot image read of the path, and then excuse me, create a what? Okay, so now I'm gonna have, let me see here, I believe three. three, three images per row. Let's say here I have two and a three. And then the first one will be our original image. So I'm gonna directly just show the image and the title. Okay, so this is the original image. I put this, the tickers, of the X, Y axis on purpose. If you really don't like it, what you can do is just, X dot axis off so that it will be no number. I want to leave these numbers on purpose because with this kind of numbers, we can kind of like measure it, that's the point. Okay, so now what I'm gonna do is I'm gonna create a K list and do the K-means clustering. So what I'm gonna do, let me write something, a note here. Let's say load and plot the original image. So here it's gonna be kind of like K means clustering and the subplots and the subplot. Let's say the clustered images. Okay, so now first of all I need to have a K list to indicate which case do I want to do, and then I will use a for loop to handle it. Here, I believe I use a 2, 3, 5, 10. Okay, so I'm gonna put 2, 3, 5, 10. Okay, so now one very important thing is I want everyone to see the shape of image. Print shape image dot shape. Okay, you can see it's a 255, 200, 201, and a 3. What does it mean? That means it includes the 255 rows and the width, which is the columns, is 2, where it is 201. It as it's RGB and hence it's a 3. The thing is, I cannot use this one to directly train. Let's say model equal to, something, what I mean this. Just to tell, I cannot do this. For K, and then let's say for I in the zip of, did I create, okay, in the zip of, K list, and then the range of the length of K list. I cannot do this. This is wrong. Model model equal to let's say K mean, let's say n cluster equal to K. Then I say model dot fit image. It will show error. Okay, and you can see that the array is with dimension 3, but expect less than or equal to 2, and hence I need to reshape this image to another thing. What we can do here is to again use the reshape function, but here I will have a special trick, which is let me create something called image array equal to image dot reshape. I'm gonna leave a -1 here. So in the reshape function, if you read the documentation, -1 means let the system determine by itself. But here is a 3. I already tell you. So what you can do, let's have a look at here. Image array dot shape. Let's have a comparison. Okay, you see it? So these 3, I tell you that because it's kind of like RGB. So I'm gonna, in other words, the first column, let me use the term, the zeros column is the R, the first column is G, and the second column is B. This means, okay, I'm gonna tell you the number of column is 2. Regarding how, it's 3, sorry. Regarding how many number of rows you're gonna determine by yourself. So what the system is going to do is the system will see, okay, since your matrix image is tensor image is 255 by 201 by 3. So I'm going to make this 255, 201 to be this first number, which is, I actually have it. You can just see it. 255 times 201 equals to this 51255. And that's how they get it. And now once I have image array, this is indeed a matrix, 2D matrix. And then now I can use model.fake image array and I just run it and you'll see it's gonna, this is a warning. You can just ignore it, not a big deal. And you can see, just you can just, okay, Python show me off. Every time I need to comment paste, I cannot remember. You need to import warnings, ignore. Yeah, you can just do this so that you can just mute the warning and then okay, here we go. You can see it's run and there's no error. So that is the thing. Sorry, it's still running. So yeah, here we go. So that's the thing. Okay, so now I'm gonna what? I'm gonna subplot this. I've already trained, right? So here I'm to get the clustered image. The clustered image means for suppose you give me a k, okay, whatever k, then I'm gonna plot the image with only this color k colors so that I call image plus third. In other words, let's say suppose it's 2nm. So sorry, not 2nm. The 2 means clustering. It should only have two colors. Then the problem is that my original image array here is the image array, right? How can I map it to the color? Of course, you can definitely use a for loop to write it, but it's actually pretty slow. It will make you to wait for a long time. So what we can do is here, since we have the model has one attribute called cluster centers. So the cluster centers means what? Means, since we have k means clustering, let's say here, suppose k equal to 2. So I have two clusters, right? So this center clusters shows you the what? The result of the clusters. So let me just, let me show something here. Okay. So let me just, comment all of this. Okay. So what I can do is this. For example, I can print model dot clusters. Here we go. Wait 1 minute. What's so large? Wait. Something is wrong. Something is wrong. What did I? What did I? Wait. I realized a pretty dumb thing. Oh, that's why. That's why. Sorry. By the way, did you realize why there are so many numbers? Recall that, here I just commented all of this, right? And I see the K list. The last K list is 10. See, in other words, here the K here is still the last one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes. In other words, here we're actually doing 10 means clustering. And this model dot clusters means, I mean, this is the result of the last training result. This is the last training result, in which k equals to 10 here. In other words, this is the 10 clusters that I currently have. So let's see. And indeed, you can see 10 rows and 3 columns. See it? 3 columns means the RGB. No worry. We will have a CMap. Make it a kind of like to be, kind of like a binary map or something, so that you don't worry about the colors. But that is the thing. Okay, so now I have the clusters. Then, in other words, let's say the 10 is clustering. That means the whole image will be composed of these 10 colors, which is right here. Be composed of these 10 colors. Okay. Then the problem is that for each image point or pixel, what color should I choose? Right? So what I need to do, what I need to use here is model dot label. So here model dot labels, label or labels. I believe labels, yes, labels. Model dot labels tells you the labels for each point actually. So I can definitely print it again. Okay, so let me just comment this again. Again, because our last time is at 10. So that you will see numbers from 0 to 9. Okay. Why it's all 7? Uh I know why. All 7 because it happens starting to start to last, because they're all black, you can see. So that I'd better show you here. It happens to be the same, you know what I mean, which is number 7. But if you see something inside, I bet you the model label because here we only have those, those numbers. And then super simple. Max, and you're gonna see 9. Min, you're gonna see 0. Oh, sorry. No, min, not max. See, you're gonna see 0. So here we go. Okay, so then what does this mean? So model.cluster center, model.labels, that means, okay, I'm gonna, for each point, I'm gonna substitute, and by the way, you can even print this. Uh, let me put a model.labels.shape. And you can see the shape is file one. I mean exactly the number we just saw, right? So this shows you that it's kind of like by Ravels make it to be a flat vector. So this is the number of for the labels. In other words, for each point here, totally we have 51 to 55 points. But for each pixel here, I have a label. What does label mean? Label means it's from cluster 0 or cluster 9. So this is it. In other words, this model, the cluster center labels, the model that labels this shows, hey, what is exactly the cluster? Say, for example, if this is a vector of this, right? Suppose for the first pixel, suppose it's this one. Suppose it's number 7, for example, 0, 1, 2, 3, 4, 5, 6, 7. Suppose the first element is 7, then model.cluster centers of this label, I will show this color. Suppose the second number is, let's say number 6, then I'm gonna have this color. You see what I mean? And now, if you just do it like this way, is it correct? Absolutely correct. However, be careful because you want to what? You want to use image show to show it, right? To this point, to this end, you cannot make it like this way. Why? Because remember, we've already reshaped it in this way. So we need to reshape it back to the images to the shape of the images, not to the images, to the shape of image. So I'm gonna shape it, reshape it back, image.shape. See here? So here, image array is to reshape to that. And then in order to plot it, I need a tensor. And hence I will shape it back to the image shape. Okay, so now I can just, simply plot it. Figure.add subplot. Here, what I have here? I forgot. Let me see where the subplot thing. Oh, okay, two number of image per row, and then one. Sorry, and wait, it should be I plus two. It should be. Yes, I is this one because I starts from 0, and don't forget we will have the original image here, so it's I plus one, which is I plus two. And here I have, so now I can use dot image show of the image clustered. Okay. Again, one thing is because you want to make it to be kind of black and white, so you will make it to be 255. I believe I wrote a note here. Let me see here. It has two modes actually. Okay, okay. You can use it like as type int to force it to be an integer. So dot int has two modes. Is the number inside the parentheses must be in 0 and 1 as a float number, or you can make it as integer numbers, which is a discrete set, which is from 0 to 255, to 256 in total choices. So here, to make my life easy, I'm gonna use this one divided by 255 to make the number between 0 and 1. So it's gonna be float, and then I can just show it. And again, to be honest, it's because I'm lazy. That's the thing. So and then x dot set title. I can say what, let's say it's gonna be like image under, let's say, k means clustering. Okay, so now I can see, yeah, now I can plot it. It will take some time because for so many images, it need to take some time. Okay, here we go. Great. Actually, it's faster than I had expected. Okay, so we can see here's the original image. Image under 2 means clustering, 3 means 5 means 10. Excuse me. 5 means 10 means clustering. And you can see, I personally love this 2 means clustering the most. Why? Because in this specific example, my point is a tumor. Of course, here's a little, I'm cheating because I know there's a tumor or something. However, if your brain has some whatever problems like this, it's probably because if a tumor, then the density of the something in the tumor will be different from the other, the density of the other part of the brain, and hence from the MRI scan, the color is different, and hence you see this. Because two means is very, very simple. It's just black and white, and hence you know what I mean. You can already see it. In practice, what doctors do is they will have a lot of training data based on the different patients. Of course, they have the data for from normal people. Normal means, I mean, there's no issues, on the brain scan of different angles. What they're gonna do is that they will run the the two means clustering here, and also they will compare the two means clustering with people normal two means normal scan under the two means clustering, and then they will immediately see something is wrong. And of course, there you need some pre-processing steps, which is to like rotate. Sometimes, for example, the head can be a little towards that direction. You know what I mean? Let me just the head may not be like this way. The head may be about this direction. So the whole plot could be something like this. Sorry, I'm really not a very good you know person to it can be it can be like this direction instead of the head like this way. So we can just rotate it, of course, scaling by scaling it to the point, but these are very simple, honestly. The point is those kind of white points. And then if we consider more parameters, we can make it to be 3 means, 5 means, 10 means clustering, and you can detect more those kind of, I actually don't know what is this protocol, but I know this is normal because everybody should have it. Otherwise, what's the term? I don't know the terminology, but I know this is very normal. So that you can, what I mean, like you can compare it. And then from under the findings clustering, you see some white points here. And then based on the size and those kind of things, you may be able to tell something about this tumor here. So that's a meaning. And we can see it's super clear. This is the one application in the image segmentation. Let me see here. One more thing I want to mention. So in my slide, a function here. So I mean, this we have seen a lot before, so nothing special. Something special for this class, in this class is here. If name equal to main. So it's, I mean, if you write a lot of Python codes, you're gonna see this is a very standard, code here, a line of code here. This means because consider I'm running a project. So remember what we said import before, right? In which lecture? Lecture one maybe or two, one probably. So I introduced the import function before. Very after I ran by import pi, I mentioned pipy. No, lecture two so far. Lecture two is Python. Here, okay. So import where it is. Okay, import library cannot show. Anyway, let me see here. Cannot show. Anyway, let me just open a local document. Uh, what I mean is class after class library. Okay, here we go. So we have those kind of import library. I can even import modules, which is a pyplot file. Remember it? And then if a project runs big, you probably will have many module files so that this sentence underline where is it's here. If name underline double underline name double underline equal to quotation double underline main double underline quotation. This means if I'm in the main function. So if I have many module functions, but your main function or your executive function is only one, and use this sentence in case I make a mistake, so that I can make sure that I only do this when it is in the structure of the main function. So that's the point. Nothing very special or very serious. If for a small project, you don't have to write it at all. You can just be careful of the indentation. By the way, you can just directly write it, but it's just a habit, in case you need a big project. Okay, so that's the only thing I want to mention for this example. And indeed, the results are pretty clear. So, and then the second thing is we can run something for fun, like a ragdoll cat here. Let me see, can I see a cat? Okay, so this is a ragdoll cat, and I can read the image to the ragdoll cat, and then we can do the same thing. Again, this is just for fun, and then wait for a little bit, and then it will show you the result of the ragdoll cats. But okay, here we go. again you can see original image after 2 means clustering, 5 means clustering. When it's about 10 means to 20 means clustering, it's already very close to the regular. However, you can actually make the image size much smaller because here you're only using 20 colors, while here you have many. You can see by our eyes, these two almost no difference. Even these two are pretty close already. I guess it's done. Okay, yeah, it's done. So that's the thing. And then the next two example is for fun because recently, when I prepared this lecture, I saw I don't know whether you pay attention to how many weeks ago that Ukraine just bomb the air some military airs of Russia, and you probably see very interesting things here. Let me just you can see Russian they put a lot of tires on the plane, and why? What the news just told you is that oh it can like make something wrong, can mislead the detection of the drones or of the satellite. But what does that exactly mean? So this is an example. So we can see here. Let me. Oh, sorry. You can see here. Let me just make it to be Russian. I can just rename it. Tires one. Where is my image? Oh, here. Let's run it. What you can see here is so this is the original image. From this image, it's very easy for me to tell this is a plane, right? However, what do you know? What you may not know is that for those drones or something, because their chips, it's drones are pretty cheap, but they are not that functional. So they typically run a very low, the colors. In other words, for example, in this 2 means clustering, suppose we didn't see all other pictures, you just see this one. Question, what is that? It's not that easy for you to determine that this is a military airplane. Not to mention, if I ask you, hey, what is the model of this? It may not be that easy for you to tell. However, if we see the original picture, you see, it's easier. In other words, by putting those color tires, especially the tire color is very close, gray color or dark color close to the ground, it can really make, those kind of machine learning AI algorithms wrong, make it unable to detect that this is a plan. So that is the thing. Okay, here we go. That's the result of the things here. You can see it's not that clear. And I will. Actually, I'm running this example already. Similar things. It's the second image, which is which one is one, which one is two. This is two. And this is one. Okay, similar thing. In this original image, it's super clear. I believe everybody can tell this is a military plane, right? Very clear. However, by putting those kind of tires on it, and then I run the 2 means clustering, the result is here. Result is here. This image it's not that clear, because why? Because all of these are dark color, and you can see the runway is also kind of like partially dark color and also those kind of white color. If I do not give you the background, I just let you see this. It's not that easy for you to tell, hey, this is clearly a military play, and then I will lock it and bomb it. So that's the meaning. That's why, soldiers they put those kind of tires on it. Actually, I have a better idea, which is can they kind of like put a cover on it? Make it a cover similar color to the runway. You see what I mean? So that I can kind of like perfectly kind of hide the plane. It's not that easy for them. I'm not sure why they put the tires. Something to some covers like the cover, hail cover for your car or something, because the cover is not that. I guess it's easy. I mean, tires are easier, I guess. I'm not sure which one is cheaper, but definitely the plane itself is much more expensive than the cover or those many tires. So this is a trick, and then we can easily use the K-means clustering algorithm. It's just for fun, to see why, because this is a very real things. I didn't get it, such examples about recent Ukrainian. So sorry, not Ukraine, recent Israel and Iraq war, if we can get some data, sometimes, if you analyze the video from the drones, you're gonna see many interesting things. Actually, you can even play it at home. Just write some simple codes, and then those kind of image segmentation, how to detect it automatically, how to correct the image, something like that. Okay, I believe this is everything about the k-means clustering. Any questions? No? Okay. Before starting the next lecture, which is a PCA, Principal Component Analysis, as a courtesy reminder, today, if I remember correctly, yes, it's today. Today is the due date of homework number 2. I have not received everybody's, homework. So if you have not submitted the homework, hurry, because the deadline is just how many 6 more hours about. So that's the thing. Okay, so then let's go to the last lecture, which is principal component analysis. I've already submitted the slides there online. Okay, let me open the local one, make my life easier here. It's called the principal component analysis. First of all, I want to introduce the concept of data dimension reduction. So suppose we have the original data, with the p features. Again, this p can be the number of pixels, let's say 1 million something. And then p typically is a large number. Data dimension reduction is a technique used to transfer a data set, containing n such data points from a high dimensional feature, let's say P, to a low dimensional space, let's say K or whatever number, while preserving the most significant info of the original data set. In particular, if the reduced space has up to 3 dimensions, so let's say 2D or 3D, then we can visualize the data, simply because, our space is 3D, so we cannot plot, we cannot directly plot more than 3D dimensions. Of course, you can use some tricks to plot more than 3D, for example, like different shapes or different color, but that's another story. Here I use a pretty vague term, significant information. What does significant information really mean? That's the issue, because like you have seen in the those machine learning models, we need to define everything accurately, in computers, so that they can learn the data. So here, significant in general really depends on the data set and the specific question. However, we can have a summary like this. A direction in the data space is considered significant or representative if, let me use the color, if, direction along which the data shows substantial variations, capture important characteristics of the data set. What does it mean? Let's have a look at the second example. The first example, sorry, here. So this is Steve Jobs with Apple. So suppose this is the original image. A half body of photo of Steve Jobs. I should say Steve Jobs and Apple. For Steve Jobs, Apple is a super significant point. So the original image has 250 times 1269 pixels, which is about 972,000 pixels. Second, the third picture is just a partial picture, and you can clearly see the resolution is much lower here. First of all, from the original picture, we can easily recognize Steve Jobs. Actually, in the first 2 pictures, both this and this. However, if I ask you, hey, suppose suppose I didn't, show you these 2 pictures. I just directly give you picture 3 and ask you, hey, what is that? Who's that guy? You cannot tell me. Why? Because what do we see is just a suit and a hand. I didn't show you Apple, because if I show Apple, you may guess it's Steve Jobs. But if I just hide it, it can be anybody. It can be you, me, or any person, right? So it doesn't show you the insignificant or show you the important, those kind of info. The representative info or the important info in the whole image is actually what Steve Jobs and Apple. That is the most important thing. So here we only have, let me see which one. The the second picture, the total dimension, the total pixels are 333. So it's already a reduction from 972 to 323 here. And yes, this photo includes those significant information, means Steve Jobs and this and his Apple. This is the important thing. By comparison, the last one, although the dimensions, is 470K pixels, it's even higher than the second picture, but lower than the first picture. However, it doesn't really show you the significant info. That's it. Then you're gonna ask me, so why in this picture Steve Jobs is very and or the Apple is very important? The reason because suppose I show, let's say, 1,000 such pictures, which is a person's half body picture. Uh, the direction change the most is what is actually the face, isn't it? Because everybody's body is pretty similar. I mean, for most people's bodies, hand or something, it's pretty similar. Everybody can just stand and show half hand, show this position like this. However, to tell the point, or to tell the significant info here is the face. And look at this directions along which the data shows substantial variation. This one captures important characteristics of the data set, isn't it? I want to see part of the data which shows, significant or substantial variation. And the part for people's half body picture is actually what? The face. Here, of course, for Steve Jobs, this specific person, Apple's another characteristics, another representing features. But it's really specifically for Steve Jobs. For example, if I, just if I just hold an Apple, that's nothing. But Steve Jobs, held an Apple, that's completely another story. Okay, so that is the thing. And another example here is consider this data set. The original 2D data set is here. And this is indeed 2D, no problem. Okay. The thing is that you can clearly see this data set, although I have so many, I actually forgot in my code how many data points, maybe 1,000 something. Let's say 1,000 data points. However, the main variation is towards this direction. This is V1 direction, you can see. And this reminds me what? This reminds me, hey, what if I just shift the center from zero zeros here, from here to the center of these points, and then I just make a rotation, and then I can consider this V1 and V2 as my coordinate space. So here my coordinate space, I use it to coordinates. I use it to be original feature one and original feature two. I can actually plot the whole thing to be V1 and V2. You see what I mean? So that I can just make this one to be my coordinates and then show the data. And furthermore is you can see compared with V2, V1 is very big. Here, I mean, here because I want to show you, so I cannot make it that large. I can, actually make the V1 much more significant, meaning that the result will be kind of like let me use another color. The result can be kind of like a line, a very flat line. In this kind of cases, what's a point for me to keep V2? I can simply use V1 to show the whole, data set. Why? Because V2, there's almost no change. I mean, the data is very close. However, along the direction of V1, the data changes a lot. And this is more significant, the so-called significant information in this data set. In other words, we can actually reduce this 2D original feature, reduce the two features to be one feature, which is I only plot those direction projected onto my V1 direction. That's it. So I reduce, here's the, dimensionality, reduce the dimensionality, which is from 2D to 1D. So this is a very, basic fundamental idea of the dimension reduction. And this already shows you actually the idea behind the PCA, principal component analysis. Okay, let's see more details here. Uh, so consider data point, which is here. Suppose that the data point, the original coordinate is, let me use another color. Let me use the blue color. Suppose the original, oh, it's too big. Make it thinner. Let's say this. Okay. Suppose the original point, the coordinate is x1, x2. I should say the data point in the original coordinate is x1, x2. Okay, so I write it in this way. I write it to be x vector equals to x1 times I1 and x2 times I2, where I1, I2 are the what orthonormal basis, and the x1, x2 are just the coordinate. So suppose let's say x1 is let's say 3, x2 is 5, so that you can write x equal to 3, 5, right? And what does x equal to 3, 5 means? That means x equal to 3 times I1. I1 is this direction, the x-axis plus x2 5 times I2. I2 is the y direction. That's the meaning. Okay, so here I can consider another orthonormal new basis. The one thing I do need to mention, I'm not sure whether I learned this in linear algebra, but the orthonormal basis means the base vectors that are unit vectors and orthogonal to each other. Here it's 2D, so I don't have let's say v1 equal to mu11 plus mu12. That means the length of this unit is called a vector, unit vector. So the length of the vector is 1. Plus they're orthogonal to each other, meaning that the inner product of if you choose any two of them, it must be 0. Here, because I only have, it's a 2D, so I only have two basis vectors as orthonormal vectors, which is v1, v2. Suppose it's in 3D, so I shall have v1, v2, v3, right? That means each vi of the base vectors are unit, meaning that the length of them, each of them is 1. Plus, you choose any two, the inner product of them must be 0, meaning that v1, v2 inner product 0, v1, v3 0, v1, v2, v3 also 0. So that's the meaning of the orthonormal to orthogonal to each other in the unit vectors. Okay, let's have a look at the 2D case. So in the 2D case, suppose I have wait a minute. Suppose here these two, I wrote in blue. This v1, v2 is my new orthonormal basis. Okay, so first of all, I can express the v1, v2, in my old basis, which is I1, I2 basis. So here I wrote that to be v1 equal to mu11 I1, which means the coordinate of this unit vector v1, if I project it onto the I1, which is the original base, is mu11. Similar things project to be I2 is mu12. So I can write v1 equal to mu11 I1 plus mu12 I2. And similarly for v2, I can have v2 equal to mu21 I1 plus mu22 I2. Again, what I'm doing here is simply just to project each orthonormal new basis v1 v2 onto my original feature space and then get their coordinates. That's it. Okay. Now the thing is, let me see. Now the thing is, what is the coordinate of x along the new basis vector v1 and v2? So I know the coordinate of x along my old basis, is x1 and x2, right? So how to get this? And actually, if you have a look at the case how we get wait 1 minute. Oh, okay, I've already showed here. Actually, this is super simple. The corresponding coordinate of x onto any vector is simply the inner product. So for example, if I ask you, say, hey, what if the coordinate here on my v1, it's simply just x inner product of v1, and here's x inner product of v2. So you can get a corresponding coordinate. I'm not sure. Have you learned this in high school? To be honest, I originally learned this in high school and not in the math class. It's in the physics class. So which is the effort? So suppose I have two color. Let's say the blue and also the red. I have two vectors. So the inner product of this and this means what? The effort that made, of this force onto this direction, isn't it? So similar things, you can consider X is a force, let's say, And then this V1 is a direction. Then I have X inner product of V1 means what I project onto it, which is the effort. So that's the thing. In other words, this point, or what I can say this way, make it even more clear. In other words, the length from here, let me make it bigger, sorry, biggest. The length from here to, this point, this length is simply the inner product, this one, X and V1. And similar things, the length of the length, from here to this point should be what? Should be the inner product of X and V2. So that is the thing. Okay, knowing this, and we have already got the a concept of projection. Let's see more examples. So from here, let me give me 1 second. Give me 1 second. Let me run it here. Here I'm gonna open an IDE called a PyCharm to run it. Simply because you know the 3D the 3D rotation something I don't matter can show more clearly. So here what you can see is we can rotate it. You see the point here. So it is oh sorry. It's really a very in longitude ellipsoid. You can see here. Let me show it again. It's very you can see this direction, let me just plot it. Along this direction, it's very long. While along other directions, it's just very kind of flat or small. So so here, I name it to be V1, V2, V2 is this direction, and V3. Our original basis is I1, which is I1 is here, original feature 1. You see here, I1. I2 is here, which is original feature 2. I3 is here, original feature 3. And then I don't have to, continue using this original basis. Instead, I can use the new basis, which is composed by V1, V2, and V3. Of course, as I showed before, technically they should be orthonormal basis. Here, in other words, the length of V1, V2, V3 should be the same. But here, just to indicate that, because I have to plot a 3D, figure in a 2D. I mean, the screen is 2D, not 3D, and hence I make the length different on purpose to indicate that the data set has the biggest variation in V1. That's the reason. And you can see we can change the space or change the coordinate system to the new basis, right? So we can make it in this way. Okay, now let's introduce about the idea of the principal component analysis (PCA). So the idea of identifying directions along which the data set varies the most and then analyzing the data with respect to these directions is called principal component analysis. And these directions of the greatest variations are called variations. Okay, not only one, because later we'll say, let's say the first K PC, so you will have K. They are known as principal components PC. Then, but what exactly does it mean for the data set to differ or have differences along a direction, say a unit vector, v? This difference can be quantified, as we mentioned, by the variance of the data projected onto that direction. Uh, in other words, for example, like here, if I have this is a training data set, I will project it, for example, suppose this is V1. Suppose we know it. Okay, I know I'm cheating, but suppose we already know it. That means, okay, look at here, the variation of the whole data set projected onto V1. You can see it's a large, right? Because if I project it onto V1, the length is kind of like, I plotted as V1. It's very long, a half length. However, if I project it onto V2, the length is only this, indicating the variance is much smaller, V3 even smaller. So using this one, we can show the difference. The difference along V1 direction is the biggest. V2 is smaller, V3 is even smaller. So that's the thing. However, to formally show build the models for principal component analysis, we need to address the following three questions, actually, three problems here. First of all, I need to find out the mathematical expression for the variation in the original feature basis. This is actually super simple. The second thing is that because here we're talking about a new basis, because we will, we will find the data sets, along which direction, varies the most. So I will have the new basis piece, which are called PC basis. In this new feature basis, what is the data? And correspondingly, what is the new variance? In other words, I'm gonna first find the expression of the variance in the original feature basis. Then I will project the data onto the new feature basis, which is the PC basis, and then I will calculate the new variance with respect to this new basis. And the third thing is, so I will have like suppose original data is P. As you can see, if I don't make any data reduction, no matter how you rotate or exchange, have the new basis, it's still the same direction, the same dimensions. So for example, if even if I change, for example, from I1, I2 basis to the new V1, V2 basis, it's still 2D. Similar things here. It's no matter how you change, how you rotate those bases, it's still 3D because here's I1, I2, I3. Here you change it to be V1, V2, V3. So what's the point for me to do it, right? So we do, as we mentioned, the principal component analysis is a technique to reduce the dimensionality of the data. We do need to find out the first, let's say, the most significant, the second most significant, the third most significant, up to the piece most significant direction since the original dimension number of dimension is p, and then we're gonna use a trick to lower the dimensionality, make it from p to k. For example, p is 10,000, k is 10, for example. So these are the things we're going to introduce from slides 8 to 14. We'll solve those problems, these three problems step by step. Okay, the very first question, the expression of variance under the original feature basis, which is question number A. First of all, we need to know the expression of, in general, if we're considering RP, okay, we are going to talk about covariance instead of variance. And the variance is going to be a matrix called covariance matrix. This is the definition of, for a P feature space, and it's P by P. I'm not sure whether you've learned this in statistics, like high dimensional statistics, so that you should be familiar with the term covariance matrix. So basically, the ijth element in this covariance matrix it represents the covariance between I and the jth features. So that's the thing. So now go back to our problem. So this is a beautiful mathematical formula definition. However, we want to what we want to have a practical formula, right? Which is given, let's say, suppose I have x1 till xn. I know these xn data points each has p features. Then I want to ask you, so suppose I have those kind of data. So what is the distribution, variance of this, covariance matrix of this? That's what I want to ask. So first of all, in order to get this variance of where y is a random variable, I assume all those data are generated from the same source, the same distribution. So first of all, I need to get the EY, and the EY, by definition, by definition is this, which is nothing but the average of these m data points. It has p dimensions. Be careful because each data point has p features. Have the feature the UI, and then I just simply use this formula, that definition again, because this on the outside there's another expectation. So again, I have n points, so it's another 1 over n. Then it's gonna be xi minus xi bar, where xi bar is nothing but the mean of all this data. And then you just use this definition, you can compute the Vy, which is the covariance matrix of the original, based under the original feature basis. That's the thing. Of course, if I use a matrix notation, I can define a z in this way, and then I can directly write the covariance matrix to be 1 over n zt z. Actually, it's nothing. It's just this one and this. Be careful. This is a z. This is a t. Okay. And if you check it more carefully, Z is actually a mean-centered version of the original data, where the mean has been shifted to be zero. Why? Because on each data, I make it from the data itself to data minus X bar, where X bar is the mean. So it's the mean-centered. That's the point. Okay, be careful for the dimensions, however, because I define it this way. So Z is N by P, and the ZT is P by N. Here, I wrote here. Be careful of the dimension. Okay, so now I've solved the first question, which is find the mathematical expression for the variance in the original feature basis. Second, I need to project the data onto the new feature basis, which are the PC basis. Here, I assume, okay, I assume I know the basis, which actually will be solved later. Then how to project? It's actually super simple. For a given vector v and the raw data x, the projection onto, from x of x onto v is just, the inner product by the scalar. Remember, you can consider it as like a physics effort. That's a thing. And then which represents the coordinate along the direction of the coordinate of x along the direction of v when v is treated as a basis vector. Again, basic vector means it's a unit vector and different bases must be also normal. Okay, now consider I project all those observed data from x1 to xn onto V. How can I make it? And then, first of all, make our life easier. Remember, since we've already discussed this, it's a covariance matrix. So I do need to make the mean centered, of each data. And then since Vy is in this way, what I can compute is for each number, each data, I will have what? I will have, a projection V here. And hence, the whole covariance matrix can be computed in this way, VTVV. Sorry, it's VT is the basis, and this V is a covariance matrix and times another V here. And, make it more detailed since Vy, let me use the term variance instead of all VVVV. Variance Y is 1 over N ZTZ. So that you have a left multiplication of the basic vector V and VT and the right multiplication of V. So it becomes this way. So just left multiplication of VT and then right multiplication of V. Done. So this is the thing. Here, vector V meaning the meaning is that it is the variance of data, random point Y under this V direction instead of our original feature basis. And be careful, this V Y under this V direction, this is a scalar. Why? Because this Y is actually a vector here. It's not a matrix, Although the whole what Y here is a covariance matrix. But the covariance matrix means you're going to project it onto different bases. But if I give you a specific direction, a specific basis, this is going to be a scalar representing the variance of the data along the direction, specific direction V. So be careful of this point. So now if I have one V already like this, I can make it to be all directions and make the whole thing. But before that, let me just show an example to verify that this formula is actually correct. Okay, so now consider two data points, which are x1 equal to 0, 2, and x2 equal to 4, 2 in our original data point, original feature space, which is I1 and I2. And then by the formulas before, it's super easy for us to compute x bar equal, x bar is super simple. 0 plus 4 is what? 2. And then 2 plus 0 is what? Sorry, 0 plus 4 is 2. Because I have two data points, so 2 divided by 2 is 2. The second one, 0 plus 2 plus 0 is 2. As I have two data points, so n equal to 2 as well. 2 divided by 2 is 1. So my mean x bar equal to 2, 1. Then the mean centered data z is just x1 minus, which is what? 0, 2 minus 2, 1, which is negative 2 and 1. And the second data is 2 and the negative 1. That's it. Then I can compute the covariance matrix using this formula, which is, so this is my covariance matrix, right? So question, what if I'm going to ask you, hey, what is the data, the variance of this, data set x1, x2 along I1? Super simple, we can just read it. It's a 4. along I2, it's 1. That's it. Okay, now what if I project the two data points onto the unit vector, which is 45 degrees, which is this unit vector, which is square root of 2, square root of 2 over 2, and then the second one, square root of 2 over 2. First of all, it's super easy for you to verify this is a unit vector. Why? Because the length of this is 1. This one square plus this one square, which is 1, so that it's a unit vector. Now we can project this x1 and x2 onto this unit vector, and then we can get the coordinate. Say x1 project onto it. I make this notation. You can just make the project of it. Then you can get the coordinate here is I wrote here the length, or the coordinate here is square root of 2. And then you project x2 onto it. The length here is I wrote here, or the coordinate here is 2 square root of 2. So that's a thing. So now if I use directly use the definition of the variance to compute of this, brutally compute the variance of these 2 points using the new coordinate system, I would be where it will be here. First of all, the mean of the projected coordinates, which is the center, the mean of these 2 points is nothing but square root of 2 plus 2 square root of 2, because I have 2 points, so divide by 2. And this is 1.5 square root of 2. And hence, directly by the definition of the variance, okay, the projected variance of these 2 points onto this v direction is, the original data square root of 2 minus the mean, and then square, plus this one minus the mean square. Remember, do you know what I'm talking about? So here I'm talking about the definition of the variance. Suppose, okay, let me move here. Suppose I have 2 points, x1, and x2, right? Both are vectors, okay? Then how to compute the variance of it? You're gonna say simple, v equal to what? A half times what? A half, because I have 2 points. Or even 3 points, it really doesn't matter. Let's say, let me use 3 points. So how to compute the variance? Variance is 1 over 3, sorry. 1 over 3, and then what? And then you're gonna have wait, let me use this. Let me use, so that what looks better. Let's see here. Wait here. You're gonna have x1 minus x bar square plus what? X2 minus x bar. I can just copy and paste to make my life just easier. Sorry about it. Let me make copy and paste. So you're gonna have x1 minus x bar square plus x2 minus x bar square plus x3 x minus x bar square. Remember, this is a definition of the variance. And then since I have 3 numbers, so divide by 3. So this is exactly what I'm doing here. So I have 2 numbers, so 1 over 2, which is the first coordinate, square root of 2 minus the mean is 1.5 square root of 2 square, plus the second number, which is 2 square root of 2, the second coordinate, 2 square root of 2 minus the mean square. And then you just compute it. The answer is 0.5. Okay, now I want to verify that this formula is correct. What I'm going to do is that, remember, we've already got a z, and I know what is a v. V is, where's v? V is square root of 2 over 2, square root of 2 over 2, right? I just plug in everything inside, and then you will get exactly the same result, which is 0.5. So this is just a baby example to show you that this result is correct. You're gonna project, because for each point you're gonna project onto it, but you are computing the variance, and hence you will have a both left and right multiplications, and hence you get this form. Okay, so now the second thing is I want to determine the principal components, because here I give you the v already. I mean, I tell you it's square root of 2, square root of 2. But in a practical case, how do you know what is this v? So it is actually a optimization. It's actually a quadratic optimization problem, which is, first of all, by definition, we just mentioned, PC's principal components are the directions along which the data sets varies the most. And hence, we actually later will see, we'll call it the first PC, the first principal component. And then if we combine the definition and also with the projection, the formula here, then we can make it to be a quadratic optimization problem, which is here. I'm gonna, V is the decision variable. I'm gonna maximize VT, ZT, ZV, subject to V is the unit vector, meaning the length of it is 1. So that's the thing. What does it mean? The meaning is exactly here, which is, hey, I want to find out a direction along which the data set varies the most, or let's say have the largest variance. While this vector, this direction is the unit vector. So this is the meaning. In other words, to solve this problem, we are to seek the unit vector V, which is the first PC that maximizes the variance of the whole data set projected onto this direction V. And the V is my decision variable. I want to ask, hey, what is this V? Of course, if you really strictly compare to this formula, you can see I have a fraction which is 1 over n. This is actually a constant. I can just ignore it. Why? Because n is observed. N is known because I give you already n, let's say 100 observed data for training. So you already know this n equal to 100. So it don't affect the location or the solution of this optimization problem. And that's the thing. And if you want to, explore more in this direction, it's actually a special case of Redis flotation quotient problem, which in which it has xtx here over xx here, because we've already limited the v to be a unit vector, so the length is 1, so it doesn't matter. Okay, then we're gonna see how can we actually solve it. The reason I want to show a little bit how to solve it because it will directly derive the expression and will be linked with the eigenvectors and eigen numbers. This I'm pretty sure you must have learned in linear algebra. So I do want to mention this point. So the trick here is called KKT conditions. Again, if you have never heard of KKT conditions, it's fine because this is not a main point for in this class. I just want to let you know that it exists, something called KKT conditions. It is actually something to show you necessary conditions for local optimality in general, those kind of nonlinear optimization problems. So here's the general form. So this fx can be a nonlinear function. It doesn't have to be linear. So we have the inequality constraints and the equality constraints. The KKT the conditions state that, if I have such a general question, whatever, F, G, H they are, it doesn't matter. Then if, X star is a local optimum, then there exist multipliers, mu and the lambda, such that all these 4 conditions holds. There are the stationary condition, stationarity condition, which is nothing but the gradient of this with respect to x plus with this mu coefficient of the inequality constraints plus this weight combination of the equality constraints equal to 0. This 0 is a vector, be careful. And then the feasibility constraints are you just copy and paste, these 2 constraints. They're called primal feasibility. And then dual feasibility is actually this mu. It's related with the so-called dual problem. And then complementary slackness here is the summation of all of these with respect to the G, which is the unconstrained, which is the inequality constraints. It must be 0. And here's a link if you're interested. You can click this to see details of the KKT conditions. Okay, so now we're gonna apply the KKT conditions to our specific problem. And since we don't have H here, which is inequality, constraints, we only opposite. Since we don't have G constraints here, which are the inequality inequality constraints, we only have those kind of equality constraints. So what I have here is only, the stationarity constraint and the primal feasibility. Primal feasibility is just copy and paste, which is, it's a unit vector. And then in stationarity is you just make the gradient of this objective function with respect to v, and hence you can clearly see this result is the projective result. It's like x squared. The derivatives at 2x, right? Several things. Here the derivative is this. And then at v equal to v1, so I substitute v equal to v1. Here we go. And then you minus a lambda 1, times the gradient of this. The gradient of this is super simple. It's just 2 mu1, v1 equal to 0 vector. That's it. And then with this, you can directly get ztz times v1 equal to lambda 1 times v1. And one point I want to mention here is that you may say, hey, look at here, here's a plus lambda. So why did you say, here I make it to be minus lambda? It should be plus lambda, right? Well, this lambda coefficient, it doesn't really matter because you can see here, we don't have any constraints for this lambda. In other words, the lambda can be positive or negative. Since it can be positive or negative, so it doesn't matter here you write a plus or minus. It's, it really doesn't matter. So the reason I want to make it to be minus is because I can get this expression. It's a very, very beautiful expression that you can, if you're familiar with the concept of eigenvector and eigenvalue, once you see this form, it immediately shows you what? Shows you that this V1 is actually an eigenvector of the matrix ZTZ. And this lambda I is actually the corresponding eigenvalue of it. Recall the thing, suppose it's the actually some basic linear algebra. Suppose let me erase everything here. Okay. Let me use a new page. Suppose I have a matrix, let's say X, and I have XV equal to lambda V. Recall what happens here? We say V is the eigenvalue, eigenvector of this X, right? And the lambda is the corresponding eigenvalue of it. Exactly the same thing. The thing is here, your ZTZ, where it is? Your ZTZ here is the X here. In other words, I immediately see that this V is actually the eigenvector of ZTZ, and this lambda is actually the corresponding eigenvalue of it, corresponding to this V1. That's it. And then now we already know there are eigenvectors and eigenvalues of the Z matrix ZTZ. Then the thing is, it generates, because ZTZ is the result of the matrix of P by P, generally has P eigenvectors and P eigenvalues. Then the thing is, which eigenvector and eigenvalue should you choose to get the first PC? Recall that here it's a maximization problem. I want to maximize this, right? And then I have a trick here. ZTZV equal to what? Remember, ZTZV equal to lambda 1 V1. And hence, I can just call, what I mean this. Let me make it small. What I mean is this part equals to lambda V1. And hence, I just, put a lambda, because lambda scalar V1 is a column vector. So I just remove this part, and then I have lambda 1 times V1t transpose times V1. Again, don't forget this. I have this constraint. This means what? This means this means V1t V1 equal to 1. Why? Because V1t V1 equal is actually nothing but the for norm of V1. And we've already seen in the primal feasibility, V1 must be equal to 1, and hence it's gone. And hence, the whole objective function can be simplified to what? Can be simplified to mu lambda 1. So to maximize the whole thing is equivalent to maximize lambda 1. In other words, my first PC must be what? My first PC V1 must be the eigenvector of ZTZ corresponding to the largest eigenvalue lambda 2, lambda 1, no, lambda 1. That's it. So in other words, as long as I just solve the problem and I solve all the eigenvalues and I find the largest eigenvalue, the corresponding eigenvector must be the first PC. That's how the mathematics tells me. Okay, then the thing is that here I have so many PCs. Technically, I can have as many as P PCs. So, well, you've already solved the first the first PC as the largest the eigenvector corresponding to the largest eigenvalue. How about the second PC, the third PC? Here, a mutual like understanding or natural understanding here is that I can actually make the second largest, the eigenvector corresponding to the second largest eigenvalue to be the second PC, the third largest eigenvalue, lambda 3, to be the third PC. Again, be careful. PCs are the corresponding eigenvectors, not a value. Okay, what I'm saying that we can define the PC to be the jth PC to be the eigenvector of ZTZ corresponding to the jth largest eigenvalue. It's a very natural like understanding of this concept. However, actually, there's a rigorous mathematical derivation of this. You can use mathematical to actually define it, based on an orthonormal basis. You can actually define it instead of just naturally like understand it this way. If you're interested, it's in section 2.1 of this of of this one. Well, I think so right here. Given the first one, the second one, the third one, and you're gonna see. Did I use induction? I forgot whether I use induction to prove it. But basically, this thing can be proved so that you can know that our guess that the jth must be the jth largest. This is actually correct. Okay, and also one thing to mention is it is actually closely related to singular values of the z. I'm not sure how many of you have heard the so-called singular value decomposition. If you have never heard, you can again go back to the extensive reading. It shows you something about that. However, since this is not the main point of this class, it's something about matrix computational theory. So I'm gonna ignore it in the class here. If you're interested, you can just read it. Okay, so now let's consider the mean centered data matrix Z. The coordinate of this Z, as we just mentioned, we can just make a production. Pay attention, okay? Z is the form of the vectors. Let me go back to the row vectors. So Z is the form of this one. So the first row is actually x1 minus x bar. That's the mean centered. But be careful, by default, our vectors by default is row column vectors. And hence I need to make it a T. You see what I mean? In other words, I just write the data to be a row. So let's say a very simple thing. Suppose my where is here? So suppose let me open a new one. Suppose my x1 equals to let me just use a 3D to make my life easier. And then suppose my x1 equal to 1. Uh, let me make it three numbers. Okay, suppose my x1 is 1, 2, 3. And my x2 equals to, let's say, 4, 5, 6. 4, 5, 6. Then you can get what? You can get your x bar. Your x bar equals to what? Your x bar equals to simply the sum, the mean of all of this. Your x bar equals to 2.5, and then 3.5, and then 4.5. That's my x bar. And then you make it to be z. You're gonna see that z equal to. So here I'm gonna write derivative this way, which is uh let me see. This number is nothing, just I make the x column vector to be a row vector, which is 1 minus 2.5, and then 2 minus 3.5, and then here the 3 minus 4.5, 3 minus 4.5. You see what I mean? Similar things. What I mean is this: just make it a transpose. Because by default all of these are column vectors. So this is z. You just consider before it's like this way. So now it's 1, 2, 3 minus the bar like that way. So here is 3 minus 2.5. Well, so sorry, 4 minus 2.5, which is here. 4 minus 2.5 minus 2.5 and then 5 minus 3.5, and then 6 minus 4.5, So this is the meaning, okay, of z. Okay, so now I have this z. I can project it onto my I can project it onto the new basis or the new feature spaces called a PC basis or PC spaces by what? By the Z multiplied by this the J's PC. Here, because here we've already seen that what is the technique to get all these PPCs? It's just by solving this problem. And actually, even don't you solve it because you already have an analytical solution, which is nothing but eigenvalues, and the solution is eigenvectors. That's it. So you just need to get eigenvalue decomposition, so you can get all those V1 till VP, right? And then you can project it, project our mean center matrix or data matrix Z onto this P. Then you will get this. And this is formally called the score of the JPC. Later you will see the what the result. I will show you by the phase decomposition example. You will see it. Okay, so now the thing is, well, I totally have p orthonormal bases, which are the PC's principal components, and the original data, the dimension is also p. If I use all of these PCs, so what's the point? I mean, I just wasted my time to do the eigenvalue decomposition, right? And then I get exactly the same data. This is correct, and hence I will not in the application I will not apply all these PPCs principal components. All of the PPCs, by the way, is called the total variance, and I mean you can simply compute it in this way, which is nothing but the summation of all the P eigenvalues. I mean, this is a mathematical, derivation of how we get this. And under these eigenvalues, actually, I don't have to apply all these P principal components. I can just apply to the first K PCs. And hence, I can perform the dimensionality reduction from the P dimensions to K dimensions. Be careful, P is much bigger than K, okay? I should say P could be bigger than K. For example, your P can be millions and your K can be, for example, 10. Like this scales, specifically if we only consider the first K PCs, and ignore the remaining P minus K PCs. The variance explained by these PC is, here your summation J from 1 to P, which means all, the total, and hence it's called the total variance. Here, your summation is J from 1 to K only, and it's called explained variance by this first K PCs. And then to determine how many PCs are equal, are adequate, sorry, because you don't want, I mean, I'm going to ask you, so what is this K? So you need to determine how many are adequate to represent the data, right? We're going to calculate the ratio of the explained variance to the total variance. And the ratio is then compared to a user-defined threshold alpha. So which is specified the desired percentage of the total variance to be explained. Finally, the smallest k satisfying this RK ratio is greater than or equal to alpha is chosen as the number of PCs to retain. Okay, let me show you an example so that you can understand much better. So suppose I have x1, x2, and x3. Here, due to a space limit, I already wrote everything to be row vectors, Okay, so and x4, x5, I have 4 data points. First of all, I need to compute x bar, then I need to compute the mean center, the z, and then compute the eigenvalues of ZTZ. So the eigenvalues of ZTZ are these 3 numbers. And with respect to these 1, 2, 3, wait a minute. Yeah, because they are 3D, P equal to 3. Each data is composed of 3 features, you can see. And hence I have 3 eigenvectors corresponding to 3 eigenvalues. Okay, so now I have these 3. I use different number to, to make it, different colors, sorry, to make it a corresponding eigenvalues and eigenvectors make it easier for us to read it. Okay, so clearly our first PC must be the eigenvector corresponding to this number, right? Because this number, this eigenvalue is the largest. Okay, and hence I got my first PC is this vector, which is this. And then I can get the individual explained variance. Individual explained variance means of PCJ means the variance explained by PCJ alone. This is actually super simple because here you can see I'm just doing nothing but the summation of all these, individual explained thing. Each one, let's say Ji, is what? It is what? It is just the eigenvalue itself. So and hence here, I already get my eigenvalue of lambda 1 equal to 468, 486.613. And hence, this is my individual explained. This is the biggest. Okay. And the second PC should be what? Should be the eigenvector corresponding to the second biggest one, which is 161. So this one, the purple one, is my second PC. The third one PC is, of course, the smallest one. So this is the third PC. Now, suppose I predefine an alpha threshold equal to 90%. I'm going to ask you, hey, how many PCs do you need to is enough, is adequate to explain 90% of the total variance? Okay, so now we compute. First of all, R1 is if we only use the first PC, it's going to be, the individual explained variance is 468 divided by the total. Total is 486 plus 161.6 plus 4.159. This means R1, if I only use the first PC, the total explanation, the ratio of the total explained variance is only 74.59, which is less than my threshold, 90%. Hence, I need to include the second PC as well. So here is, 486 is, individual explained by the first PC, then the individual variance explained by the second individual explained variance of the second PC is 161. So my numerator is going to be 486 plus 161, and my denominator is going to still be the total variance. And then we can get a ratio of 99%. So we already get more than threshold 90%. And hence, I'm going to take k equal to 2, meaning that we can reduce the dimensionality of the data sets from 3D to 2D while explaining over 99% of the variance. However, if my threshold is only 70%, and you can see I just need R1 because R1 is already greater than 70%. And hence, in this case, I only need the first PC. That's it. So this is the whole logic and mathematical model of my principal component analysis. If you're interested, you can try to code it by yourself. And honestly, it's not that difficult at all because NP, the NumPy library, already has everything, including the eigenvalue decomposition, including the eigenvectors. It's actually pretty simple. But we're lazy, right? So we can directly get something via the scikit-learn. Let me close the PyCharm. We terminate. We can directly get the thing from a scikit-learn, and we can just simply get everything here. So let me see. In this example, what we do here is I need to wait. I need to open another class, which is lecture 10. Another lecture 11. Okay, so first of all, I need our old friend, the NumPy. And then I will have from scikit-learn dot decomposition. Forgot decomposition. Yes, import PCA. Decomposition import PCA. Okay, now first of all, let me just randomly generate some data. Let me open the cheating mode. I cannot remember the data points. X equal to mp dot array. Here I'm gonna just have some arrays 10, 11, 10, 5, 3, 6. Let me add a space here. 9, 0, -2, -9, -12, 10, And then the last number is 5, 0, -2. Okay, so I can just train model equal to PCA. And then, of course, you can write, something like the number of components which we will use. But here, suppose I just want a complete, decomposition, a full decomposition. So it will have, three PCs because your original data is 3D. And then I can make it to be what? Wait, I believe these are the same number. Sorry, I just moved to another screen. These are the same numbers here. What I'm doing is I just want to use, use the what? Use Python to scikit-learn, library to direct get this result. Actually, you know what? These things I did it via MATLAB. I didn't use scikit-learn, but they're going to be the same thing. Okay, so model equal to this, and then let me see where it is. Model dot fit x. Again, there's no label y because it's unsupervised learning, and I can make PCs equal to model dot components. So here, what I'm gonna do is I want to print the PCs. Oh, forgot one thing, which is np dot set print options. Okay, which is a precision equal to 3. So first of all, I'm gonna print all the PCs, which is PCs, uh, and then we can have a look at it. So these are all the PCs, my 3 components. You can of course make n components to be 2. Then actually you can see it shows you only 2 PCs. By default, if I don't put anything there, it assumes it's a full decomposition and a full eigenvalue decomposition as it's gonna show 3 PCs. And next, I showed you each explained variance in each individual explained variance. So this is by model dot explained variance ratio. No, it's just a variance. Since I've already set up the what precision, so this is fine. And then I'm gonna print the individual, ratio of it. So this means, by each of these individual explained variance, how much, ratio among this total explained variance can I get? So it is just individual explained variance ratio. And this is the model dot explained ratio here. It's all, already built in. So so that you don't have to, like really everything, write a code by yourself. And then finally, I want to print the coordinate of the here x dot shape of this many data points in the new PC basis or in the new PC feature space. Here, let me just transform. Okay, transform X. Okay. First of all, these are the 3 PCs, which are just the 3 eigenvectors of the matrix ZTZ. And they explain the variance are these, and then explain the ratios are this. Remember what we just got before? Let me make it smaller. The previous slide, you can see they're the same. Today it's gonna be over. I will show the what show the MATLAB. This one I need to install it. I believe I already on my in this computer already don't I probably don't have the MATLAB here. So here let me see here, and then indeed you can see 74.6%. You see here, which is 74.59%. And the second one is 161.628 divided by the total, which is 24.8%. And indeed, if you sum these two, you're going to get about 99%. The last one is only 0.6%. That's the thing. And then, as we just mentioned, well, if your threshold is 90%, then you need the first 2 PCs. But if your threshold is only 70%, then the first PC is already satisfied. Okay, then this is the coordinate of the 5 data points in the new PCs, which is well for my first, the original coordinate of the 5 PCs are, for example, the first data is 10, 11, 10, second data is 5, 3, 6, right? Okay, now I project it onto the new PC feature space. Then the coordinate in the new PC feature space, my coordinate is negative 10.18, 7.917, and negative 0072. This is actually nothing but, you just compute this, the z times vj. Or geometrically, if you want to know the meaning, it is that I have x1 here, x2 here. Now I create a new coordinate system. I want to project x1 to v1, x2 to v1, and then also x3 to v1. In all these systems, what I mean is this. Where's what I mean is this. For each data point, original coordinate in the original feature space is x1 and x2. In the feature space, I1, I2. Be careful, I1, I2 are vectors, okay? Now I'll create v1, v2 space. Question, what is the coordinate if you project this data point onto your new PC system? It's going to be, this down one and this one. Of course, here I have the 3D so that you're going to have three numbers, but the meaning is exactly the same, which is a project, all these, all these for each number, I project it onto my PC space, which is v1, v2, v3, and I get the new coordinate system is this. And the second one is the second data. The third one is the third data points. That's how you get it. By the way, one thing I want to mention is remember the score. Score is something, you just project onto it and a new coordinate system, right? And this you can simply just use, this dot transform, and then you will get the coordinate, or just, you got the new scores. You can just read it. You don't have to compute it because I mean the second library Python computed for you already. So this is the score for the first data point, score for the second data point. So that's how you can make it. Okay, since today the time is already about 7, I'm gonna end here since I don't believe I can finish the next, examples. It does take some time. I will stop here. And then I will see you on Thursday for the last lecture of this class. Thank you and have a good night.